Swayam Prabha. Digital India. Educated India.
In the last lecture, we started discussing on the Euler-Bernoulli beam based formulation, and then we looked into a specific case which was a symmetric actuation case where same voltage is applied at top and bottom. Here by same voltage we mean the relative direction of the voltage and the polarization. So, in this case it produces either a contraction or a tension depending on the relative direction of the polarization and voltage and the D31 and the D3 coefficients, D31 coefficient. Now, we got this relation EA total epsilon 0 is equal to n plus NP, and this equation is sufficient to solve it because the other equation does not come into picture because this is symmetric case. So, ES total is 0. Now, we will look into the displacement that is caused here. So, let us assume that there is no externally applied load. So, N is 0. If NP is there, then how do the beam deforms? How does the beam deforms? That is what we want to see now. So, EAB del U 0 del x is equal to 0. That is the equation which we can write in this zone. Now, in the piezo zone we can say EAB plus EAC del U 0 by del x is equal to NP, and here we have x 0 else x is between x 0 and x 0 plus LC. Now, please understand here EAC is the has the contribution from both the piezos, and then again beyond that piezo zone we have EAB del 0 by del x is equal to 0. Here x is more than x 0 plus LC. So, if we integrate the first equation we get EAB U 0 is equal to C 1. If we integrate the second equation, that gives me EAB plus EAC U 0 is equal to NPX. It is better that we bring the denominator at this side. So, then we can write EAB plus EAC NPX by EAB plus EAC, and there is a constant C 2. Here it does not matter because anyway it is 0, and then in the other side or this here also better absorb the constant in this side and call U 0 as just C 1. So, C 1 by EAB, that is one constant, let us call it C 1. And then we have again for the last case U 0 is equal to C 3. So, this is when we have x between 0 and x. This is when we have x between x0 and x0 plus LC, and this is when we have x beyond x0 plus LC. Now, we have to apply the boundary conditions and the continuity conditions. So, here we have three constants C1, C2, C3, and we have three conditions. Displacement is 0 here, the displacement is continuous here. So, whatever displacement we get from this side, it should be same from this side. Similarly, whatever displacement we get from this side, it will be same as what we get from this side. So, if you put these conditions, it gives me C1 is equal to 0. So, C1 is equal to 0 because u at x equal to 0 is equal to 0, that gives me C1 equal to 0. And then if we apply the condition that displacement is same here and here, that gives me that NP x0 divided by EAB plus EAC plus C2 is equal to 0. So, C2 becomes minus NP x0 by EAB plus EAC. So, this tells me that U0 is NP divided by EAB plus EAC x minus x0 when x is between x0 and x0 plus LC. Similarly, when we put the other condition that the displacement is 0 at this side, that tells me that U is equal to C3 is equal to NP by EAB plus EAC multiplied by LC when x is beyond x0 plus LC. So, if we draw the graph now, it would look like this. If I draw the displacement graph, so initially the displacement remains 0, then the displacement varies linearly, and then the displacement remains 0. So, the value here between this is NP by EAB plus EAC multiplied by LC. Now, if we solve this problem, so where I have another boundary condition at x equal to L, if you want to solve this problem, it becomes a statically indeterminate problem, because we cannot find out the reaction here. So, it is a statically indeterminate problem by degree 1. Now, if you want to solve this, then what we can do is we can decompose this problem into two sub problems. In the first case, let us assume that it is only fixed at one side and we have only this, and then in the second case, let us assume that it does not have the piezo, but it has the reaction from the support, and let us call it R. I mean sorry, it has the piezos, but the voltage is not applied here. So, here we have VV and here we do not have any voltage, and then if we superimpose these two results, we can find out the displacement here in terms of this R, and then we can say that the displacement is 0, that will give me the reaction R, Once we get the reaction R, we can find out all the other things. So, let us call it 1, let us call it 2. So, for 1 we have u at x equal to L. So, let us assume that the beam has a length L. So, u at x equal to L is N p by EAB plus EAC multiplied by LC. We have already solved this problem. Now, for this we need to look into this differential equation, where we have EAB del u 0 by del x is equal to minus r, because of this everywhere the normal force is r when it is, and then EAB plus EAC del u 0 by del x is equal to minus r when we have x 0 plus LC, and again we have EAB del u 0 by del x, it is del, is equal to minus r when we have x greater than x 0 plus LC. Again we can solve it problem, we can integrate these 3 separately, it will give us 3 constants. We can specify the boundary condition here, displacement is 0, we can say that displacement is continuous here, we can say that displacement is continuous here. That will help us get all the constants. After we get all the constants, we can find out the displacement here. All right. So, let us give it a name. So, find u x l in terms of r, and let us give it a name delta 2, and let us call it delta 1. Now, the total displacement should be 0, which means if I combine the displacement that we get from this case plus this case. So, delta 1 plus delta 2 should be 0 actually, because we have a support, and from here we can find out r, and once we can find out r, we can solve the problem, we can find out the displacement at any point in this bar. Now, we will go to another case that is also a kind of antisymmetric actuation. It is, the beam is symmetric in terms of the properties, but in terms of the actuation we can call it antisymmetric. So, if we give a voltage V here, we are going to give a voltage minus. So, now we will look into another problem where the actuation is antisymmetric. Now, the beam is symmetric with respect to the properties. It has the piezo placed at the same place at the two opposite ends of same properties, but the voltage is actuation is opposite. So, if we give a voltage V here, we give a voltage minus V here. Now, here we are not concerned whether this V is causing tension or compression here, or this minus V is causing compression or tension here. Whatever it is, the formulation remains same. Only thing is that they are opposite to each other. Opposite means if here the voltage is aligned to the polarization in the same direction, here the polarization and voltage in the opposite direction. If here the voltage and polarization is in the opposite direction, here they are in the same direction. So, needless to say, if I get a free strain epsilon p here, we are going to get a free strain epsilon minus epsilon p here. So, epsilon p 1, which is the epsilon p here, is equal to epsilon p. Here we do not have any free strain, it is inert. Here we have opposite free strain minus epsilon p. Again the problem is symmetric with respect to geometry and material properties. So, we can say that E s total is 0, and so among these equations E a total epsilon 0 plus E s total kappa is equal to n plus n p, and E s total epsilon 0 plus E I total kappa is equal to m plus m p. Because this is 0, this is 0, these two equations are uncoupled, and here because the actuation is antisymmetric, it is not going to cause anything. So, we can solve this problem separately. Now, so E a total is not needed here to solve this problem. We need E I total, and we already know how to find out E I total. We have 3 layers. So, we just apply the formula and we get this. So, whatever the contribution comes from these two pizzos, that is absorbed in EIC, and the contribution to EI total from the beam is absorbed in EIB. And then MP is just this EC BC TC, TC plus TB, V by TC. So, here T is a subscript C. Now, in the form of two parameters psi and theta b. Psi is the external stiffness ratio EC BB TB by EC BC TC, and theta beam is the beam thickness ratio. So, beam thickness by actuator thickness TB by TC. So, this expression is written in a more, I would say, parameterized form, parameterized in terms of theta b and psi as this. We can parameterize as we need for anything, and then many a times when the actuator thickness is quite small as compared to the beam thickness, in that case also terms like TC cube appearing are 0, that kind of approximations are also made several times when TC is much smaller than TB. Now, we will study the deflection of the beam for this kind of problems. So, here we have the governing different the equation that governs is EIB delta W by del x2 is equal to 0 when our x is greater than 0 and less than x0, and we have EIB plus EIC. Again EIC has contribution from both the pizzos. It is del 2 W by del x2 is equal to MP. Let us say that our MP is 0, and this is valid when x is between x0 and x0 plus LC, and then we have EIB del 2 W by del x2 is equal to 0 when x is greater than x0 plus LC. So, if we integrate the first equation, it gives me, again we do not need to have this EIB in the left hand side. So, we have del W by del x is equal to C1. Then for the second equation we have del W by del x is equal to MP by EIB plus EIC x plus C1, and for the third equation we have del W by del x is equal to C3. It is a C2 constant here for the second case. For the third case it is C3. And now we can again integrate it once more. So, this is when 0, this is when x0 is between x and x0 plus LC, and this is when this, and this is last one is when x is beyond x 0 plus L C. If we further integrate, we get C 1 x plus C 2, here we get M P 2 E I B plus E I C x 0 2 x 0 x square by 2 plus C 2 x plus, okay, we have already used up to C 4 C 3, so it is C 4, and then we have C 5, and then here we have C 3 x plus C 6. Again this is between 0 and x 0, this is between x 0 and x 0 plus L C, and this is beyond x 0 plus L C. Now again we have to apply the boundary and continuity conditions. Here the boundary condition is slope is 0 here, slope should be continuous here, slope should be continuous here, displacement is 0 here, displacement should be continuous here, displacement should be continuous here. So I get 6 equations and I have 6 unknowns to solve, C 1, C 2, C 3, and then C 4, C 5, C 6. So after we satisfy these 6 equations, then these 6 unknowns are determined, and after doing that the solution that we get is this. So delta W by delta X we can write after applying the boundary and continuity conditions. So we get delta W by del X is equal to 0. There is no slope when my x is between 0 and x 0. Then we have delta W by del X is equal to M P multiplied by x minus x 0 by E I B plus E I C when my x is between x 0 and x 0 plus L C, and then we have del W by del X is equal to M P L C by E I B plus E I C when my x is greater than x 0 plus L C. As far as the displacements are concerned, there is no displacement at the beginning. Then we have M P x minus x 0 square by 2 E I B plus E I C when we have x between x 0 and x 0 plus L C, and then we have W is equal to M P L C square by 2 E I B plus E I C plus M P L C by E I B plus E I C multiplied by x minus x 0 minus L C. So if we draw the slope graph, it would look like this. So it is 0, then slope varies linearly, and then the slope remains constant. And if we draw the displacement graph, so it is slope, so it is I would say del W by del X graph, and if we draw the displacement graph, it would look like this. Initially displacement is 0, and then there is a curvature. So, so you would see some curvature here, and then this slope, and whatever the slope here is, this would continue. So, this part is curved part, it has a curvature. So, this is W. So, in this zone from here to here, del 2 W by del x 2 is equal to 0 and del W by del x is equal to constant, and within this zone del 2 W by del x 2 is equal to constant. So, here I have a constant curvature and it gets some slope here, that same slope continues. So, it is a straight line after that. Now, we will go to another problem where we have asymmetric actuation, and this asymmetry comes because we have put one actuator just at one side. So, we do not have any other actuator here. So, that is why the problem is asymmetric. Now, when we have just one actuator, this is going to induce both bending and in plane displacement. So, it will have both response and we have to solve it. Now, this problem can be solved in two ways. In the first approach, what we do is we consider the mid part of the beam, which is this mid part of the beam. Let us consider that as our z equal to 0 line. Now, with respect to this point, if I find out my ES, it would be non-zero. EA total, as we can find out, EB BB TB. So, area of this multiplied by the corresponding Young modulus plus BCTC and multiplied by the corresponding modulus, it remains same. Only thing is that here the contribution is from only one side. ES total is this. So, ES total is this, and then we have EI total, and NP is this, MP is this. So, the free strain in the beam is here epsilon P. Then we can write the combined equation, which is this. So, we have both NP and MP induced and ES total are non-zero. So, we cannot solve the equation separately. We have to solve the coupled equations, and after solving the coupled equations, we will get epsilon 0 and K both, and that will give our displacement. So, we will have both non-zero displacement along axial direction and non-zero displacement along the vertical direction. Now, let us talk about approach 2. In approach 2, we look at the actual physical neutral axis of the beam. Now, because this beam is asymmetric, so if we draw a cross section here, the cross section might look like this. Let us consider that the width of the beam and the piezo are not same, just to be more generic. In this case, the neutral axis shifts up. So, we consider this neutral axis as our z equal to 0 line. Now, how I found out the neutral axis? To find out the neutral axis, all we do is just evaluate this integral. So, it is, we know how to find out the centroid. If we forget about this E, rest of it is, if we put E is equal to 1, rest of it is just the formula for finding out the centroid. Now, to find out the neutral axis, all we are doing is we are putting a weight, and this weight is just the Young modulus. So, instead of having z dA, we have E as a function of z into z dA integrated, and here just having dA integrated, we have E dA integrated. So, that gives us the position of the neutral axis, which is z bar, and then accordingly we can find out EA total. Then if we take this as our z equal to 0, and then if we find out our ES total, it would come to be 0, and then we can find out our EI total, and after this we can find out NP and MP. Now, the problem has become like this. So, ES total has become 0 because we have found out it with respect to the physical neutral axis. So, ES total is 0. So, this equation EA total multiplied by epsilon 0 plus epsilon 0 is equal to NP plus N, and we have another equation EI total multiplied by kappa is equal to M plus N. Now, these two equations can be solved separately and the results can be superimposed. So, again results should be same. So, we will find out, we will have both axial and vertical displacement, but the advantage is that we do not have a coupled equation. So, solving these two individual equations are easier than solving a coupled equation. So, with that we would conclude this lecture here. We will look into more cases in the future lectures. Thank you.